So, hello everyone. My topic is for stochastic sample model on complete bipartite graphs. So let's start. So first of all, we have sample models. This is one model about many sand grains, and then we put some sand grains on each vertex. Based on the sand grains, we can try to do some dynamics on the sample models. So firstly, we have the sample models. It is initially introduced in the study of the self-organized criticality, and then they try to develop it into a Billion sample model. We call them ASM on general graphs. This one is also called chip firing game or dollar game. We also have stochastic sample models. We call them SSM. This is one stochastic version of the ASM because we can add the additional randomness. So our main goal is to study the stochastic sample models on complete bipartite graphs. So first of all, we have the complete bipartite graphs. We have two sets of the vertices, top set and bottom set. Here we have one special vertex. We call it the sink. We use label V0T to denote that. And for other vertices in the top set, we use the label VIT to denote each of them. So for the bottom set, we use the label VIB to denote each of the vertex. For the edges, we just connect each vertex in the top set and the bottom set. The sample configuration on the complete bipartite graph is one assignment with each vertex, which means we just add some sand grains in each vertex. We use C equal to CT and CB to denote that. Here, CT means one configuration from C1T to the CMT, and the CB is from C1B to CMB. Here, the CIT or CIB means the number of sand grains in each vertex VIT or VIB. Here, we use this notation to denote the set of all the configurations on the complete bipartite graphs. The top vertex VIT is stable if we have CIT is less than n, and also we say the bottom vertex VJB is stable if we have CJB is less than n plus 1. Otherwise, we call it unstable. Here, the stable means the number of the sand grains should be less than the degree of the vertex, also include the sink. If all vertices can be stable, we call the configuration C is stable, and we use this notation to denote the set of such stable configurations. So for the unstable vertices, they should start to topple. For the toppling rules, we use the co-flipping model. Here we give the details. So we first have the toppling probability P, and then for each neighbor of the unstable vertex we just draw the Bernoulli variable for that. For example, if we have BW equal to 1, we just have the probability P, and we send one green from the unstable vertex to the corresponding neighbor, and we use the color blue to denote that. So here the vertex V2T is unstable, and we send one green to the neighbor V2B, and then we use the blue color to denote that. And also, if we have the probability 1 minus P, we just keep the current green and we don't send to the corresponding neighbor. So here, the vertex V1B should not receive the green from the unstable vertex V2T because we have the green color. After that, we can find the vertex V2B is unstable again. And here we have 3 blue edges. And recall we have the blue color for the probability P, and then we just send the corresponding one green to each of them. And we have 1 minus P for the green edge, so we don't send one green to the corresponding vertex. So here the vertex V1T should not receive one green. And then you can notice that the sink will also absorb the one green from the unstable vertex. So after that, we can find the V2T is unstable again. And here we have 2 blue edges, which means the 2 neighbors can receive the corresponding green from the unstable vertex. So we can send one green to V1B, and also we send one green to the V2B. So after that, we can find any vertex in the whole configuration is stable, and we reach the stable configuration. Here we use the STO step to denote the stochastic stabilization of the configuration C. So after that, let's introduce the dynamic in the stochastic sample models, we first have the positive probability distribution mu. We have from mu1t to mu-mt. We also have from mu1b to mu-nb. And also here we have the Markov chain on the set of the stable configurations on the complete bipartite graphs. And then each time we just randomly pick up one vertex V. And then based on the corresponding probability distribution mu, we just add one green. And then we try to stabilize the configuration. In this process, we have two randomness. The first one is just what we have shown. Each time we just add one green to the randomly picked vertex V based on the probability distribution mu. And the second one is that the toppling rules is random. Here it means we can send some greens to the random subset of the neighbors. Also here, if we use the standard abelian sample models, we only have the first randomness, which means we don't have the random toppling rules in the standard abelian sample models. Okay, so here we have one special configurations. We call them stochastically recurrent configurations. That means in the stochastic sample model dynamics, we can find one type of configurations. They can appear infinitely often in this dynamics, so we call them stochastically recurrent. We also use the STORAC MN to denote the set of SR configurations. We also define the level, which means we calculate all the sand grains in the top and bottom configurations, and then we minus all the edges between the top and bottom configurations. So here we want to find the stochastic sample models in some graphs, but basically if we want to try the general graphs, sometimes general graphs can be very difficult to check all the subsets of the vertices. So we want to transfer to the complete bipartite graphs because we can have symmetry structures in the complete bipartite graphs. So we can choose that to go straightforward. For our study, the first step is to try to sort the both bottom and the top configurations in the weakly increasing order. And then we use the sorted rect to denote the set of all the sorted recurrent configurations. But here we have one question. How about the combinatorial description of the stochastic sorted recurrent configurations? Here we can try to use the Farrow diagrams to represent them. So let's go to the Farrow's diagrams. This is one collection of all the cells, and then we just put each row based on the increasing order from bottom to top. And then we have two categories. The first one is all the set of Farrow's diagrams with only M columns and N rows. The next one is the Farrow's diagrams, but should have at most M columns, but with the same N rows. We also can calculate the area of the Farrow's diagrams. This one is also equal to the number of all the cells. So if we have the weakly increasing sequence S from S1 to Sn, we just find the Farrow diagram Fs if we can find Si cells in each row I. From bottom to top, here we have one example. If we have S equal to 0, 1, 4, which means we can have 0 cells in the bottom row, and then we have 1 cell in the middle row. Finally, we have 4 cells in the top row, and then we can calculate area equal to 5. Here we have two operations in the Farrow diagrams. The first one is shift, which means we can shift 1 cell from current row to the row below that. Here is one example. We can shift this cell in the next row in the blue color. And then the second operation is add, which means we can add 1 cell in the right side of the current row. Here we can have one example. We add a new cell in the bottom row, like the red color. So if in this process, we can get a new Farrow diagram based on the initial Farrow diagram, we call these two operations are legal. So this example we can get from F113 to F222 based on the two types of the operation together. We also have one new definition. If we can get a corresponding new Faro diagram like this, the new F222 based on the initial F113 with the with the sequence of legal shift and add operations, we call this pair is compatible. We also have a new definition. This is the key vector from key 1 to key n. Here, each element kj means the number of elements in the top configuration who can be less than the index j. So based on this definition, we can just try to transfer the top configuration ct into the key vector. And then we can get our result. If we already know the configuration ct and cb, we can first calculate the key vector based on the top configuration ct. And then we can just go to the bijection from the set of the stochastic sorted recurrent configurations to the set of the compatible pairs with two Faro diagrams, F and F prime. After that, we calculate the level of the configuration C. This is the area of the Faro diagram with the CB diagram minus the area of the Faro diagram with the key vector, which is also is the number of the add operations in this legal sequence from the K diagram to the CB diagram. So let's go to one example. If we already know one configuration C in the sorted order, so here we have CT equal to 0 to 2, and CB we have 2 to 2. So we first need to calculate the key vector. So let's go to the first one. So let's calculate how many elements who is less than 1. So we can only have the 0. So for our key 1, we have 1. So let's go to calculate how many elements who can just be less than 2. So we can only find one element. So let's go to our key 2, also equal to 1. So finally, how many how many elements who can be less than 3? The answer is 3. So our final key 3 is equal to 3. So finally, we get our key vector, which is 1, 1, 3. And then we just try to use our legal sequence of the shift and add operations. So we first have the key diagram with 1, 1, 3. And then we first shift the cell in the top row to the middle row. And then we get this new diagram. And then we use the add operation to add the new cell in the right side of the bottom row. And then we get a corresponding CB diagram. We can just check. We have 2, 2, 2. Just correspond to the CB diagram, to the bottom diagram. To the bottom configuration CB. And also we can calculate the level of the configuration C, which is the area of the CB diagram, which is 6, minus the area of the key diagram, which is 5. So we get the result, which is 1. Okay, so finally, we want to introduce the directed acyclic graph, which is DAG. This is one collection of all the Faro's diagrams, and then each one should satisfy the area should be greater than m or equal to m. So here for each pair f and f prime, we try to put an edge from f to f prime if we can use the shift or add operations between them. Here we use blue color to denote the shift edge, and we use red color to denote the add edges. And then we use the DAG to denote the corresponding DAG we can get. So this is our example for the corresponding DAG with m equal to n equal to 3. So here you can find all the blue colors denote the shift operations. And then all the red colors denote the add operations. And here you can find the DAG is bipolar, which means we have one unique source with all the cells in each row, and then plus the with all the 0 cells in each row, and then plus the top row with m cells. And then we have one unique sink F here. So in each row we have m cells. And then we can we can get one bijection from the stochastic sorted recurrent configurations to the corresponding pairs of the Faro diagram pairs, F and F prime. But here we need to make sure the first Farad diagram F should have m columns like this, because if we go back to use our key vector, maybe this one, you can find the last character kn should be the number of all the elements in the top configurations. So we can just use the m columns in this initial Farad diagram F, and then we can just get the directed path from F to F prime if we use this DAG. Also, the calculation of the level is also equivalent to the number of red edges in this corresponding path. Okay, so that's all of my presentation. Also, I want to thank our nice organizers for this very excellent conference, and also thank everyone for being here. Thank you so much.